At the end of the last video, I was able to get the Larson scanner working here, the Knight Rider effect. My LEDs are sliding back and forth, and while I was pretty happy with that result, there were some challenges and some issues. The circuit itself is not as clean as I'd like it to be. There are some issues on starting up and some issues with, say, switching it from automatic mode to manual mode. It has its challenges there. And I was not able to explain several things, and that's really, in my mind, the bigger failure. I need to be able to understand this thing that I'm building, and if I can't explain it, then I certainly don't understand it. So today I've got a list of things that I'm going to get into. I'll go as far into this list as I can, starting with an explanation of what's going on over here with the control circuitry. And then I'm going to get into some of this timing and some issues with startup. Let's get into it. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Okay, I'm zoomed in here in hopes to make this a little bit clearer. The control bit, which selects between which of these two groups of 16 control signals, is handled by bit 5 on this EEPROM. That signal comes to the latch, which then is this yellow signal here, which comes out and down here to this XOR gate and is jumped over here to a second XOR gate. So this is going to be input number 1 of that XOR gate. Now, in the previous video, I was misunderstanding, or I had these hooked up, I should say, such that 5 volts was being, or 1 was being fed into the second XOR gate, and 0, or ground, was being fed into the first one. And then these two signals come off, and they are both connected to pin 5. That's 1, 2, 3, 4, and 5. And again over here, this is going to be pin 5. 1, 2, 3, 4, and 5 is right underneath this yellow wire. Well, if you look at the pin diagram for the 74LS138, and I'll have that up on the screen for you, pin 5 is an active low enable signal. So how is that significant? With main bus group 0, which is this group here, I need a 0 to be presented on this line, which means that I need that signal to be buffered, which is what the low signal does. For group 1, I need a low on this signal, which means that I need to take the high bit and invert it so that when group 1 is selected, that bit 5 is high, it gets inverted, the signal then becomes low, and that gets presented properly to pin 5 of this group. Now, in my defense, if I go back and look at the video itself, the video says that I had this identified as group 0 and this identified as group 1, and I made a decision in that video to change these to be reversed and did not update these signals. And so if it is a 0, the output is here. That will come down here to, this point right here, which then activates that small group. And then the inverted, so if it's a 1, it's going to get inverted to a 0, and then that'll come and drive that group there. Is that a good defense? No, but it certainly explains what I was seeing, and it also explains why it worked when I switched it, and I can now properly explain what's going on here. So I can remove this. This was just a flag to call my attention back to it. And what I'm going to do is I'm going to replace this line, this control signal here, which comes down to the main bus assert on the fetch register, with a proper hard wire. The next thing I want to take a look at is the power on state. If I flip this over to the manual clock, the circuit has been powered off for several hours, so all the capacitors should be drained. So if I power this on now, the automated clock is still running, but my program counter has a non-zero value in it. My R1 register has a 0 value in it, but my fetch register has some value in it that is really not related to a reset. And therefore, if I clock this once, what happens is the first and latch that happens here latches some different value. So now I'm going to get something else that happens in here. And this never progressed on, so my next clock didn't do anything either. And then finally I get back to my 0 address, but I've got some odd value in here. And now I've got my first load immediate. Oh, it actually did load that in there. That's not the way that always works out though, because I can unplug and reset it. I have a different address here. I'm back to my one here, but you can see that I've got the actual instruction that made it from the fetch into the register. So my challenge is, this may yet still be a timing issue, but because the circuit starts in an indeterminate state, I have no way to force that into a known good state before I start. I need to build something like that. Now, I have reset lines here, which is this yellow line that can be moved to a high signal and then a low signal. I've got the R1 registered tied low, which is never resetting, and I can reset the two registers, but that does nothing for fetch. It does nothing for the instruction register. And so I need to work out a way to do that, and I think it's going to require several clock cycles to make sure that everything is cleared. What I have here is a single pole, single throw, normally open momentary switch. So that's a mouthful. So basically, there are 4 pins on it. There's a left side, top and bottom, and a right side, top and bottom. The left side is tied together, so both these pins are actually one pole, and the right side is tied together. Both those pins are actually one pole, and when I push the button here, it actually connects all 4 pins together. And so what I want to do is I actually want to pull this to a low state. And then, let's see here. I want to extend that low state to this reset point. You can tell I keep my temporary hookup wires in a baggie. But then I also want to extend it over from here, I'll just use this one, to this reset point. So that if I push the button, whoops, I guess I need to hook up 5 volts here. So hooking that up there, now when I push the button, this is pulled low by the resistor, and my 5 volts is hooked up to this other side so that when I push the button, it clears the registers. Now, what I need to do is I need to push the button and clock once to make sure that everything actually clears. And this did not. Why did this not? Because I need to pull up. No, that should work. That cleared that time. Now I am expecting this to clear, but because I've got a 0 address that's showing up here, it's actually loading the first instruction. And that's okay. I'm going to dig out a little bit of a longer wire or 2 shorter ones. I've got some that I can join these together and make one longer wire. What I should be able to do is take this same signal here, so that is still the clear, and over here on the EEPROM, turn that so that it is not output enabled. Actually, I'm going to put it in this one, and I'm going to hook that back up, because what I believe I pulled, and I'll have to pull up a pin diagram to make sure, is the chip enable. And so I really want to pull the output enable. Now there's something with that that's not right. That's because it's still pulled low over here. Now that clears that, but when I clock, what I'm not getting is output. So that should be low. So if I tie that low, I'm getting output. If I tie that here, I am not getting output. If I tie these two together, I am not getting output. So what would happen if I instead, and I'm just going to put this right here, if I use the resistor to pull up instead of down. And then this gets pulled to 5 volts. So when I push the button and clock, it will clear. Now I'm not getting an increment here, which tells me I'm more than likely still holding this in reset maybe. Clear is the one signal I don't have an LED on. Let me grab my logic probe here. So my reset should be here, and that is not connected, or it's not showing a signal. High, but not low. So what happens if I take that low and I hit the button, the whole circuit will cut out. So I can't do that, but what I can do is try this as a pull-up instead. And that is not enough to clear. That tells me I probably have a voltage problem coming off of this pin. 4.85, that should be enough to trigger a reset. But it is not. So what I need to test is when that's hooked together. That should still be, I think that's not quite low enough. But if I hit the button, let's take that off of it and see how this behaves without it. So that appears to be working. So if I reset, well, I'm resetting here, but I'm not resetting here. So why is that not resetting? Where's reset coming in? Reset is on the... Oh, I have to reset and latch. There it is. I gotta learn my own circuit still. So reset and latch a couple of times. Let go of the reset. Everything is clear. This is the value that's in address 0. Fetch register is clear. Instruction register is clear. Clock once, and it's not incrementing. Okay, I am so sorry. Obviously the circuit is working again. I had a short of 2 wires over here, which had come apart. It was literally a dead short, so that's why it wouldn't power up. And then I had some trouble with the pull-up resistor, or sorry, the pull-down resistor here. And I did some measurements, and I put in a 220 ohm resistor here and measured the voltage of my reset signal over here on my PC. And with 220 ohms, I got 0.22 volts. For a 1000 ohm resistor, I got 0.86 volts over here, which was not enough to actually bring the circuit out of reset. A 10,000 ohm resistor ended up giving me 1.21 volts. So the higher the resistor, the higher the voltage. So what follows here are some conclusions I'm drawing based on my observations. I spent a couple of days and several hours trying to math this all out and make it make sense to me objectively, and I was not able to do so. But I did take an LS193 IC, plug it into a breadboard, add power and ground to those terminals, and the clear pin was backbleeding 1.6 volts back out of it from inside the IC. So I believe my conclusions are reasonable, but I cannot state definitively that they are fact. So I could use some help in the comments, please. And it dawns on me that I'm using LS logic. And because I'm using LS logic, I have a pull-up resistor in each of these ICs, which means that if I put a pull-up and a pull-down on the same signal, pull-up being in the IC, I put my own external pull-down on here, I end up with a voltage divider. And the voltage at this node right here between the pull-down and the pull-up ends up being some varied voltage. Now, when I reset and I clock a couple of times, everything goes back to a reset state. But what I just figured out is that if I clock once, the program counter doesn't advance yet. But it has loaded the instruction register in. I'm sorry, the fetch register for address 0. I'm still asserting address 0, and my bus, my memory onto the fetch bus, is asserting the same value. So this is a timing concern, and it's with the registers, and it's with both of these registers that I have this concern. One of the things I did in the beginning is I said I wanted to take all of the logic associated with timing off of these modules and build it all in here. So what that gives me is that gives me the flexibility of addressing this here in this module to make sure that I get the timing correct and not have to redo any of my design here or here. That's in theory anyway. So with this done, what I'm going to do is I'm going to get this cleaned up and wired up more appropriately. So let me get this cleaned up. Next up here today is I want to get some measurements of some timings between several of these signals. The first one I want to try to tackle here is going to be the program counters and latch signal and compare that against the address bus 1 assert signal. These are the registers, the actual latch, and so I'm going to put the, I'm going to put the yellow trace in here, so I'm measuring that signal, and then the data available on address bus 1 is really what I need to look at because the address bus 1 is constantly asserting. So I'm going to pick the least significant bit there, bit 0. Zooming in here, my trigger point here is on channel 2. And that's because I'm only taking a trigger when the least significant bit here changes. And so if I move back, well, criminy, to about the same spot here on the yellow trace, I've got roughly between the AND latch and the data becoming available, I've got roughly a 24.5 nanosecond delay, which is appropriate. The next one I want to look at is the PC increment signal, which is going to be down here. Start with that. And I want to compare that with the AND latch. So AND latch is actually where I was. But if I look at these traces, the blue trace is the AND latch, and the yellow trace is the increment. And the problem is the increment is actually coming ahead of the AND latch. So if I look at that looks like it's coming 11 nanoseconds early. So I really need to delay that AND latch signal a little bit. And that's a problem. The next one I want to look at is the fetch bus data available. So I'll take the yellow one, and I'm going to say the data is available when, let's go up here, when bit 0 has data. And then I want to compare that to the fetch register latch. So the latch signal is here. And that is a huge delay. That is a 100 nanosecond delay. That is massive. So what that's telling me is I'm latching this far too early for this EEPROM memory to keep up. The next one I want to compare with is the instruction register suppress. So that is going to be on here. And that's going to be compared with the instruction register latch. And that latch is way up here. I need to relocate my ground. All right, so the latch is again coming before the data is available. So if I delay both of these latches, I should be in reasonably good shape. And that ends up being about 16 nanoseconds slow. And the last signal I want to test is going to end up over here. And I want to compare the register 1 load. Actually, I need to measure those over here. This ought to be fun to do. Okay, finally got something here. My load line was the yellow and the AND latch was the cyan, and the AND latch is coming barely after the load, which may not have enough time to propagate from the counter chips all the way out. So I believe this follows in line with the other AND latch, and it really just needs to be delayed a little bit. Let me check my propagation delay. Okay, what I found here, I'm using an HC on the PCB at 5 volts. Typical is 18 nanoseconds to propagate. So once again, I am early. So I have some timing issues that I've got to sort out here. Okay, the first thing I want to try to tackle here is the AND latch delay. My AND latch signals are coming off up here. This was a previous attempt from a couple of videos ago to try to get that Larson scanner working. And so what I'm going to do is I'm going to drop this in here, add power and ground. And then all I need is a buffer delay. So 2 inputs of the XOR gates are going to be pulled down. So I'm going to actually do input 2, not input 1. Or B, I guess I should say, as opposed to 2. My outputs are going to just simply come over. And then a couple of wires here, hookups. My outputs from the NAND are going to come over to be inputs 1. And so let me reset here, and we'll see how my fixes did with changing those signals. Okay, so once again, I want to set the yellow trace over on the program counter to be the increment signal, as I'm having trouble getting that onto the breadboard. Okay, and then let's should be able to get the trigger set right. And then the second signal, I want to hook into the latch. So the yellow trace is the increment and the blue trace is the end latch, and it's still not coming in at the good timing. So let me see if I can do any better with that. I'm grabbing some hookup wires here, and I'm just going to go for an additional delay here. And that still looks not fast enough. It still needs to be delayed another 7 nanoseconds. So I guess the question becomes, do I use an inverter now? Okay, this is not labeled. but that is a 74 LSO4. If this works, I'll come back around and label that. Get power and ground in it. I worked so hard to make sure that I had these timings right, and they aren't, which is frustrating. And that significantly delayed it. Start of the rise is now 9 milliseconds. So removing an XOR gate didn't change that delay at all. Now I really don't want to go through the hell of trying to measure this one again. But what I do need to do is I need to reset. Let's put this in manual step mode. Reset. Hold the reset and clock a couple of times to make sure that everything's clear. Step number 1. But it did not increment and latch. Okay, I'm looking for time difference here-ish. 13 nanoseconds, and I need 18, if I remember correctly, for LS or for HC logic. So I do need this extra delay up here. All right, and LS is 18 nanoseconds delay. And I've got 23 there. Let's just start at the bottom. It's 19. Still don't have enough of a delay. All right, so that's quite the delay I've had to build into this program counter, which is not what I expected to have to do. So I reset everything down. First clock step increments this. I've already loaded the first instruction, which is at address 0. I've got on deck here the value to move. I clock again. This is the instruction. This is the value to move. And if I clock again, it got moved. This is the next instruction on deck. A no-op got passed on there, which is appropriate. There's the move instruction. There's the value. And it does get moved. So that helps tremendously. But I've had to build quite the delay in there. Now, my challenge is, and I may have made a tactical error here, my challenge is keeping this consistent for HC logic. If I'm going from breadboard using LS to PCB using HC, I may have made a tactical error on measuring timing. And that's where my concern falls in now, is making sure that if I am doing all of this, I'm measuring it properly. And I've got to think about this now, because before I commit all of this to PCB, I should be good. But I'm going to have to rebuild all of this logic with HC technology so that I can measure it properly. This should be good to convert because I managed my timings over here the way I had intended. This should be good. Well, I haven't addressed any of those timing concerns yet, but I have a feeling they've sorted themselves out. I will measure those in the next video. Well, definitely some surprises today. I really was not prepared for all of this delay to have to be built into this circuit. I have not yet cleaned this up, obviously, and I will look at that again in the next video. What I'd like to do is take a look at all of the different ICs that I have here and see if there's a way that I can actually delay this a little bit better, more effectively than I have it now. I don't have yet the measurement of the delay at the PCB, and we'll need to take a look at that. As difficult as it was to measure, I need to redo that measurement and see just exactly how bad that delay is and see if it's delayed more than it needs to be. Right now, the delays between the program counter and the R1 register are asymmetric. The program counter delay has been significantly longer by adding in extra inverters to improve that delay. So in the next video, I will take a look at this again. I want to measure this delay, and I definitely want to take another look at all of these signals and remeasure those to make sure that I've actually got the signals that I'm looking for. It's working far better. I feel far more confident in the reset now, and I can move on to some of the other things that I've noticed as well, trying to put together the Larson scanner. Before I move on to build any more circuitry, I've got to make sure that all of this gets stabilized. So I don't want to add problems on top of known problems. We'll see you soon.